Today's goal is to name the domain and range of a variety of function families, all of which we've learned about so far this year. Domain means the x values your function is allowed to use, and the range means the y values that your function is allowed to use or does effectively. So let's start with polynomial functions. Our most basic polynomial functions are y equals x squared and y equals x cubed. And we know that x squared is a parabola with a vertex at the origin. And these arrows here imply that the function is moving both left and up, and both right and up. Because it's moving forever left and forever right, that's why we say its domain is negative infinity to infinity. But we notice that although the function moves up in both directions, it doesn't go below the y value 0. So its range starts at 0 and includes 0. That's why we're using a bracket, not parentheses. And then continues forever upwards. That's why it's going to positive infinity. Note that we're always using parentheses, not a bracket, around infinity because you can never fully reach it. Now x cubed has this shape. And this arrow here is implying that you're going left and down. This arrow here, although the function is quite narrow, implies that the function is moving right and up. And so because the function is going forever left and right, that's why we say its domain is all real numbers. And because it's going forever down and forever up, that's why we say its range is all real numbers, or the interval from negative infinity to infinity. Now, rational functions are, I think, a little bit more interesting. For example, let's say we have a rational function with a vertical asymptote at 2 and a horizontal asymptote at 1. Maybe it looks like this. It's got some intercepts, and it's, of course, getting closer and closer and closer to the asymptotes as the function goes. Now, having a vertical asymptote at 2 means that 2 is not in the domain. So there are two different ways to write this. You could either say x is not 2, which implies everything other than 2, or you could say, equivalently, that the domain is negative infinity up to 2, union 2 to infinity, meaning everything other than 2. But 1 is the value missing from the range. That's why we would say the range is either y is not equal to 1, again implying absolutely every number other than 1 is used. So these are ways of expressing the range. Now let's look at a radical function. For example, let's say we've got a radical function with a vertex at negative 2, 3. Okay. Because the x values start at negative 2 and then move forever to the right, the domain is negative 2. We're including it, unlike the rational function where we're using parentheses to represent values that are not in the domain. So in this radical function, we're starting at negative 2 and moving forever to the right, and the range starts at the y value 3, including 3, and moves forever to the right. Now, domain and range is easier, I think, in some ways to pick out when you have a graph, but what if you're doing it algebraically? So, for example, what if I ask you, name the domain and range of the function f of x equals 2 times the quantity x minus 1 squared plus 3. Well, you would have to know this is a quadratic function. You have to know that a quadratic function has the shape of a parabola, and you have to recognize that this parabola has a vertex at 1, 3. Now that's enough to give you a really rough sketch of the function, but you know that the leading coefficient being positive means it's concave up, not concave down. And you know it has a vertex at 1, 3, so that's enough to say, okay, the function is continuing forever to the left and right, so its domain is negative infinity to infinity, but the range starts at the y value 3 and then goes up from there. So our range includes 3 and starts there, so from 3 up to infinity. Let's do another example. Name the domain and range of the function f of x is negative 2x cubed plus 7x squared minus 9. Now, I don't know exactly what this function looks like, but I remember if it has odd degree and negative leading coefficient, it has this general shape, as opposed to odd degree with positive leading coefficient. And if it has this general shape, it is continuing forever to the left and forever to the right, and it's continuing forever up and forever down. So that's already enough information to say the domain and the range are both all real numbers. Notice that I need to know enough about the shape to make a really rough sketch. I personally think visually is the easiest way to identify the domain and range. So let's look at a rational function. Let's say 2x plus 3 over x minus 4. You have to remember that discontinuities are caused by trying to divide by 0. You cannot let your denominator be equal to 0, which means x can't be 4. This is your domain. Of course, if you want to write it in interval notation, you are very welcome to do so. This would be the same thing. And you've got to remember, okay, for horizontal asymptotes, I'm thinking the numerator is degree 1, the denominator is degree 1, so they grow at the same rate as x is approaching positive or negative infinity. So I know that this function has a horizontal asymptote at y equals 2 over 1, or y equals 2. Therefore, the range is everything other than 2. Or negative infinity up to 2 union 2 to infinity. As opposed to, let's say, if I change the denominator to be x squared minus 4, in example 4, change it back. Now, again, to find the domain, you know that the denominator can't be 0. So we'll factor since it's quadratic. And so the domain would be x can be anything other than positive or negative 2. And we're looking at the horizontal asymptote. I see that the denominator has a greater degree than the numerator. So as x approaches positive or negative infinity, the y values will approach 0. This is my horizontal asymptote, which means that the range is y is everything other than 0. That's the y value you can't have. Finally, let's take a look at a radical function. Let's name the domain and range of this guy. 2 root x minus 3 plus 4. I know that the positive leading coefficient means it has this shape, and the vertex is 3, 4. So that's already enough information to say, okay, my domain starts at the x value 3, and goes off to infinity. The range starts at the y value 4 and goes off to infinity. Now, if I changed it just slightly and I asked you, what's the domain and range of h of x is negative 2 root x minus 3 plus 4, this function has the same vertex, but has been reflected across the x-axis. So again, the domain still starts at 3 and moves to the right. This time the range starts at negative infinity. You're always reading bottom to top, and its highest y value